Okay, other important equations for the least squared regression line is when you have to find the regression line and maybe you're not given slope and the y-intercept, maybe you're only given standard deviation of x and y, maybe you're only given r, which is correlation. This equation here is very commonly used. It's on your formula sheet. It's probably the formula that you will refer to most on your formula sheet that you'll actually use. And its slope equals the correlation r times the standard deviation of the y divided by the standard deviation of x. That's how you could find slope if you aren't given it. Now you'll use this a lot of times when you have a computer printout and they're not giving you slope, but you still have the standard deviation of x, y. So remember that's how they're going to be related. Also, you'll use this equation, which is confusing to look at first, but all it's saying is the point x bar y bar, which is the mean of the x's and the mean of the y's, is always going to be a point on your regression line. So if you have the slope and you have the and you're looking for the y-intercept, remember we call y-intercept A, you could plug in y bar, x bar if you have the mean of the x, y's, and you could find A to plug it back into your equation. It would be very useful. Okay, so here's a good example of where r squared comes from exactly. The coefficient of determination, remember what that's called. R is the correlation coefficient. R squared is the coefficient of determination. Is the fraction of the variation in the values of y that is accounted for by the least squared regression value of y on x. Now that sounds crazy. But all that means, if you look right here, SFE is the standard, is the sum of the squared errors, which just means the sum of the squared residuals. SST is the sum of the squared totals, which here y minus y bar, y minus the mean squared. Let me get rid of that. Oh no. R squared tells us how much better the least squared regression line does at predicting values of y than simply guessing the mean of y for each value in the data set. Consider this example was about body weight and whether or not it could predict backpack weight. And notice if we didn't know people's body weight and all we had to predict it was right here, this line is the mean line, the mean of the backpacks, that would be the appropriate estimate if all we knew was a bunch of backpack weights. We would approximate anybody's just by using the average. So R squared is telling us how much better is it to use this line, this green least squared line, as the prediction instead. So if we look right here on this fathom, shows the sum of the squares. Here's our squares. And all the squared residuals for that. If we sum up all these residuals here, we're getting the sum of the squares to be 83.8. So that's how all of our residuals squared and added up together. However, if we use the sum of the squares from the least squared line, instead we're at 30.9. The area of those squares is much smaller, so that variability has been improved. Our prediction, of course, is much more accurate using the least squared line instead of just the mean. So this comes in, our sum of our squared errors was that 30.97 value. Clear this. And our sum of our squared total was the 83.87, and that gives us this fraction right here. And if we divide it, we get 0.368, which means 36.8% of the variation in path weight is unaccounted for by the least squared regression line. So in other words, if we subtract that from 1 over here, that gives us our R squared. 63.2% of the variation in backpack weight is now accounted for by the linear model relating backpack weight to body weight. So in other words, this is now all that variation we can now account for by adding in that extra variable of body weight instead of just predicting it with the mean, which is very good. Of course, the larger your percent is, the larger your R squared, the better your prediction. Okay, a couple things about correlation, meaning R. Correlation and regression are powerful tools for describing the relationship between two variables. When you see these tools, be aware of their limitations. First thing, very common in multiple choices, is the explanatory and response. The distinction between the two is important in regression. But notice, look at these R's. Here's our R squared, 60.6, 60.6. If I change, here my X value is NEA, and here my Y value is NEA. If I switch those X and Y, our R values have not changed any. Some other things will change, but it does not affect correlation if you switch those X and Y values. Another thing that, remember, the least squared line, slope, and the y-intercept, and R is only used to describe a linear relationship. It doesn't make sense to describe a curved relationship, for instance. R is talking about a linear relationship. And that's why, again, when you describe it, you talk about that strength, direction, and form, but the form will always be linear when you're talking about R. Note also the difference between your outliers and your influential points. Here, an influential point at this child 18. Here, an outlier at this child 19. And notice your lines are not resistant to those points, and your R is strongly affected. Here was our original R with all the data with negative 0.64, and here was our original least squared line. And notice, without that child 19, which was an outlier, our R is becoming stronger if we remove that one, and of course, because the points are now closer to the line. And the slope is changing, but only slightly. Removing that outlier, it has such a strong residual, it's not going to change the slope much. It's mostly going to change the correlation. Whereas the point here, if we remove child 18, look at the large effect it has on correlation. It becomes, if we remove that point, big change in the in our R value. It's a much weaker relationship, and as well as a very large change in the slope, because that point is an influential point. It's pulling that line towards the point and really affecting where the slope of the line would be. Last thing, remember, association does not imply causation. We also say a lot with this that correlation does not imply causation. We used the example in class about the amount of rum sold in New England states versus the amount of Protestant or Methodist ministers, and how that was such a strong, linear, perfect, almost slope of 1, or R of 1 rather, between the two. But there was an extra variable there, and that was population. As population was increasing, the amount of ministers was increasing, and the amount of rum was increasing. It didn't necessarily mean as you were adding ministers, it was causing more rum to be purchased. So remember that the correlation or association does not mean that one is necessarily causing the other. They might just be related because of a different variable. Thank you.